everyone. My name is Bertrand Irisu. I am the CEO and co-founder of Brainome. It's my pleasure to welcome you to our third webinar on the benefits and applications of our measurement-based approach to machine learning. Before you get started, I just want to remind you that we have a couple webinar series. If you can go to the next slide, please. This one is the third of our benefits and application series. We have three more coming up on a weekly basis, although we will be taking a break during the Thanksgiving week. We also have in parallel a Cortex series that comprises of three different technical presentations which go into more depth in our measurements and the math behind them. Please do sign up if you're interested on www.brainome.ai/resources/events, as mentioned at the bottom of this slide. If you have any questions, please feel free to put them in the QA channel. Today's webinar is a little longer than typical, so we will, if the questions are relevant, we will actually kind of interrupt our speaker and bring up the questions during the presentation. Otherwise, we will answer them at the end of the webinar. Our topic today is the benefits and applications of working with time series data, and will be presented by Lynn Chase. Lynn is a VP of Product Management at Brainome, which means that she's laser focused on making our Daimensions users successful. She's earned her PhD in computer science at Carnegie Mellon in 1997. And she's been working on making AI software useful in the real world ever since. She joined Brainome a few months ago, bringing with her an extensive multi-decade track record of development and deployment of AI technology in business environments. So Lynn, without further ado.
Thank you, Bertrand. I'd like to start today's webinar by talking about a few examples of time series data. And the first one that we're going to take a look at is the use of human speech to do prediction. The human speech waveforms, there's an example of one here on the screen, are typically captured in about 10 millisecond time segments. So the granularity of data available when you digitize human speech is usually down at the 10 millisecond granularity. The periodicity of information in a human speech waveform is not periodic over the entire segment that's sampled typically, but there are many important periodicities that are nested and hidden or partially not visible at different levels of granularity at different time scales inside the waveform. And those periodicities are localized given what's going on as the speech going on physically and in the acoustic environment as the speech is being generated by a talker and then recorded. There are also some very interesting secondary factors that come along with speech that are used for creating predictors when you're working in a supervised machine learning world like we are. And some of those might typically be, where are the phoneme boundaries on the timeline? Where is there a k? And where does the a start? And where does the t start in the word cat, for instance? So maybe this is the word cat. And one of the things that we might get as additional secondary data would be, where are those time boundaries? And also the labels on those phonemes. We might actually have data that's been labeled so that we can know where the various phonemes are that show up in the speech segment. And the overall classification that might be being done based on this human speech, and this is something that we have seen in working with our customers, is things like predicting whether or not the speaker has Alzheimer's, or predicting whether or not someone has depression or anxiety based on the data that's found in the speech signal. So there's one great class of problems that are definitely time series problems and are great examples of working with time series data. Here's another whole category, working with financial markets and making predictions about what's going to happen in financial markets. The time scale on time series data in the financial market domain could be milliseconds if you're doing real-time trading applications. Or it could be years out if you're trying to do overall market analysis or overall market predictions. So it can vary wildly. The example we have up here is sort of on the month scale. We're looking at an example of an individual stock price over a number of months. In terms of periodicity, we would hope that there really isn't any segment level periodicity. You don't really want a stock price that's going up and then down and then up and then down and then up and down in a sinusoidal fashion. Instead, we're not looking for necessarily periodicity at the full cycle level, but there are almost certainly partial periodicities in local segments and for hidden components underneath at the noise level of sensitivity, meaning some of the underlying variations that are happening that are driving the overall curve are probably happening at a level of variation that's very maybe even smaller than the level of noise in the signal. So that's a special challenge in time series data in financial markets. With financial markets, the secondary factors that might be available to us from a machine learning point of view could be almost anything, for information on what's going on with trading with other instruments, to descriptors of the money supply levels as being managed by the Federal Reserve Bank, to weather, or to retail indicators, what's going on in the shopping world. So there's really almost an infinite amount of possible secondary information that could be used in doing supervised machine learning for time series data in the financial markets domain. The classification problem that we might be trying to address might be as simple as whether or not there's a buy or a sell recommendation on the stock in the next 10 minutes. But it could also be, and this is something we do see sometimes, a multi-class classification problem, because many times in the financial markets world, what you've got is a bunch of attributes or elements on which you're going to make based on which you're going to make predictions. But the output is very often a real numbered, smoothly moving value. Maybe it's a number that varies from 0 to 100 on the output. And so typically what you would do with that kind of data would be to do regression. But the tools that we offer, and then the Daimensions measurement tools that are super powerful, right now, they only work on classification problems. So to work with data on which you would normally do regression using our tool, we encourage you to cast the regression problem into a classification problem. And you can do that by, quote unquote, bucketizing the outcomes. And so, for instance, if the output variable varies from 0 to 100, you can cast that regression problem into a classification problem by setting up buckets. For instance, you could create an output bucket that goes from 0 to 10, and another one that goes from 11 to 20, and another that goes from 21 to 30, etc. And there are no limitations on how many buckets you would create, how many multi-class classes you would create. The only limitation is that you need to have a minimum amount of sufficient amount of data for each bucket in order to make that work. I'll get to that in a minute. But anyway, the point is that classification in these kinds of financial markets applications of using Daimensions with time series data might be as simple as a thumbs up, thumbs down, buy or don't buy, but it also could be something simple like low, medium, and high. So it could be a multi-class problem that only has a few classes in it, or it could be a heavily bucketized output that has hundreds or thousands of class labels, because you have enough data to support that. So all of these are options. Here's a third example, which is distinct in some important ways from the previous two examples. This is for developing healthcare or medical devices, often which are wearables. And often they're dealing with measures of how the human body performs that are periodic in nature. This happens to be a picture of an electrocardiogram, the electrical impulses that are coming out of a pumping human heart. The time scale on this, the little green boxes here are 40 milliseconds. So it's not as precise as human speech, but it's down there in the granularity being, sub-second. And the secondary factors that come along with a periodic function like this can be either qualitative or they can be quantitative information. So for instance, in addition to knowing what the function is and how the function is performing and characterizing how the function is performing on a periodic basis, you could actually add qualitative information: age, sex, weight, most recent blood pressure. And in terms of periodicity, we certainly hope in the case of a heartbeat that it is periodic, but not too much. It turns out that with respect to heartbeats, you want some irregularity from beat to beat. If you start seeing heartbeats that are absolutely the same every time, then that's actually a particular form of disease. So anyway, those were 3 examples that I shared in detail. Let me just share at a higher level some other examples: forecasting retail sales, forecasting economic performance, predicting the evolution of networks, predicting weather, predicting impacts of climate change. These are all very important time series problems. Some of the common challenges that come up with dealing with time series data, the first 3 are very common, are that the data sets are typically very large and they have what we would call high dimensionality. That means that there are a lot of attributes in the data, so lots and lots and lots of columns. And also, in some cases, there are also many, many, many rows, many instances, many samples taken. And so that's just something that's true of time series data in general. Fortunately, Daimensions is very well prepared to deal with very large and very highly dimensional data sets. Another thing that is very common in the time series problems is that the raw data is often very dense, yet the values from point in time to point in time can often be unique. Let's just take a look back at the EKG to talk about what that means. So these little blocks are 40 millisecond blocks. When we digitize this, we're going to get one data value at every 40 millisecond juncture. And some of those data values are going to end up being the same. Those pretty much like there'll be a couple of zeros in a row. But the actual values that you attain as you move through the function, they're going to spread out across a lot of possible amplitudes. And so oftentimes what you end up with time series data is that you do use the raw data as part of what you're creating as your attributes for your data set, but oftentimes the values that are measured are unique, even though there are a lot of them. And so that can pose some problems for machine learning software. Again, Daimensions is well suited to dealing with that, but it is a well understood challenge in the time series data world. Another thing that's very common is that the underlying phenomena that are happening in the real world that are creating the data values that are being measured and then that we're trying to find patterns within, they're often non-stationary, meaning that the cycles that are happening, the means change, the variances change, the expected values change over time in ways that are pretty much unpredictable. And that's what makes, in particular, things like trying to make predictions in the financial markets extremely challenging. And so what we're going to talk about next is how can you actually work with this kind of data to successfully build predictors using supervised machine learning. There are also, and this 4th bullet point here is kind of more of an edge case, and I'm probably not going to go into it in too much detail, but sometimes in time series data, we are limited to n equals 1 sampling, meaning we only get one sample from a particular problem. Or sometimes we can get multiple samples, but the sampling windows are unreliable. And those are challenges that are very difficult to deal with. And so I'm not going to talk about them in too much detail, but I did want to give a nod to the fact that that can sometimes come up with working with time series data. I just want to remind you before we get into the detailed advice I have about how to use Brainome and Daimensions on time series data, that really the basic thing that's going on with Daimensions and with Brainome's approach is that we have invented a way to measure the learnability and the possible generalizations and the possible risk of overfit in data sets before you actually build a model. So we can do very rapid, very thorough measurement of a data set in comparison with a decision tree or a neural network ahead of time before we build. And if you have any questions about what we mean by this, I highly encourage you to go back and take a look on our website at the archived CoreTech 101, 201, and 301 webinars, or we're about to repeat the cycle of those webinars again on Tuesdays between now and the end of the year. So you can actually join us live if you're interested in understanding why I'm making this very strong claim that we have the ability to now measure learnability of data against types of models before we build the models. That's the key idea about why this works. So now we're getting into the part where I'm giving very specific advice about how to use dimensions on time series data. There are really only two requirements. One is that you find a way to characterize your time series data so that the data has fixed dimensionality. And what we mean by that is that you know exactly how many columns there are and you know what those columns are. There can be a whole lot of them. There can be tens of thousands of them or more, but you have to know what they are and you have to be able to measure each one of those for every instance. The other thing is that you can do as many class labels as you want. You can create a multi-class predictor with as many output classes as you want, but there need to be at least 100 instances of training data per class. So those are the only two requirements. Otherwise, there are really no restrictions. You can use any number of columns, meaning you can have as many attributes as you want in your data. You can create as many data features as you want. And you can have as many rows as you want. You can sample as many examples as you want in your training data. Another thing that's really different about the way dimensions work is that the way dimensions works is that there's no need for you to worry ahead of time about whether or not the features that you're putting into the data, the attributes that you're creating in your data, are independent from each other. There's not a requirement. Dimensions does not assume that that's the case. Again, you can have any number of classes and any mix of types of data in the data set. You can mix floating point numbers with integers, with text and characters. And you can provide a data set for training that has any density or sparseness on the other hand. It could be very sparse, it could be very dense. Either way, we're good with it. Again, just a reminder about what's going on fundamentally with the innovation that Daimensions and Brainome have brought to the machine learning world is that through direct measurement that happens before you build a model, you can now know when you have enough data. You can know when you have the right data features. You can know whether or not you're going to overfit. You can judge what kind of machine learning model will work best. In this case, we're choosing between decision trees and neural networks. You can know how long it's going to take to train if you do decide to build a model. And you can know which of your data features are actually impacting the predictive power of an eventual model that you might build. And you can know all of this before you build a model. So from an engineering perspective, what we're going to encourage you to do is to set yourself up so that you can go through very quickly an iterative cycle where you pick a data design, meaning an amount of data and what are the features in the data, and then you run measurements, and then you adjust either the amount of data or what are the features in the data, and you run more measurements. And you do that, you iterate very, very rapidly so that you can quite quickly come to the point where you're ready to go and build a model. This is brand new in the world. This happens super fast with Daimensions. And the power that this brings to working with time series data is unprecedented. Let's talk about exactly what we would do to design data features on time series data. And this is the point in the presentation where things get a little bit dense. And so if you have questions while I'm presenting, I'm going to encourage you to pop those questions into the Q&A channel. And Bertrand may interrupt me to make sure that we get through with perfect clarity on what we're trying to say here. So let's imagine we have some arbitrary time series data that we're working with. I'm not even going to tell you what this is in the real world. It really doesn't matter. A couple of things I want you to notice though. I have fixed, this is one sample. So this whole page here, This whole thing that we're looking at corresponds to one row in a data set. And I have fixed a sample window. I've said all of my samples are going to be 150 nanoseconds long. Now, the first thing I'm probably going to do is just try to put all the raw data into the data set. And I'm going to arbitrarily, as I'm going through the process of designing data features, I'm going to say every nanosecond I'm going to sample, and that's the value I'm going to put into the data set in the first row for the data set that I'm building out. So in this case, I would have my first 150 columns in the data set would be the sampled values every nanosecond out of this signal. Now I'm going to try to add additional features that give additional information about how this signal is performing in a mathematical sense. So I'm going to arbitrarily say, I want to add 1, 2, 3, 4, 5 more features. I'm going to go from having 150 columns to having 155 columns. And what I'm going to do is I'm going to arbitrarily say that I'm going to look at the window that goes from 0 to 50 nanoseconds. And I'm going to pick the minimum value of the function in that window. This is me just arbitrarily saying, I think this might be a good data feature. So I'm going to take the sample, I'm going to look at that 50 nanosecond window, and I'm going to find the minimum value. And that's going to become feature 151 in my data set. I'm going to move that window to the right by 25 nanoseconds. I'm going to calculate the minimum value that I see in that window. And I'm going to add that as my 152nd feature in the data set. I might be off by 1. It might be 150 and 151. You can do the math. But you get the point, is that I've decided that I'm going to create new features for my data set by setting a window width and a delta slide increment, which is 25 nanoseconds. And I'm just saying, okay, I'm going to start with just adding the minimum value that I see in that window. Now, I could add additional features as well by adding the max value that I see in that window. Or I could calculate the arithmetic mean over that window. Or I could calculate the root mean square value over that window. Or I could calculate the number of zero crossings over that window. Or I could run a linear regression across that window and enter the slope of the line. I can do whatever I want that I think characterizes what might be going on in the shape of the curve in this window. And for each one of those calculations, I get a new data feature depending on what the window width is and how far to the right I slide it, what my delta increment is for the slide. Now I've done that at one level of granularity. I've said 50 nanosecond windows are interesting to me for some reason with a 25 nanosecond slide. But I can also, in addition, or maybe as a substitution, I can also change, I can use the same window length, but I can change the delta slide. Or I could change the window length to a much shorter period and the delta slide to a much shorter period and create a whole bunch of, and again, with each window, I can calculate whatever I want, min, max, arithmetic mean, RMS, slope of the line. I can do whatever I want to create new features for my data set. What I'm doing, again, is I'm experimenting with what should the data features be that actually, when I apply the Brainome measurements, give me information about whether or not those data features are doing what I want them to do. Are they helping me gain accuracy? Are they helping me gain generalization? That's the questions we're asking. Does my choice of data features by going through this process change whether or not I'm overfitting? That's the beauty of the process. I can do whatever I want in terms of designing the data features. And I can go through an experimental process with the dimensions measurements to figure out whether or not I'm converging on a data feature set that makes sense for the information that's present in the samples that I'm taking. Now, just a reminder, this was for one line, one sample in the data set that I'm creating. I would then repeat that to build out the data set by resampling whatever the underlying phenomenon is, again, at the 150 nanosecond time window. And then I would repeat whatever I had done to create the data features. I would just do that for every sample that I take. And that's
Lynn,
how it. Yes.
Okay. If I can interrupt, I have a couple questions here,
Sure.
which I think are appropriate. Coming from Don, the first question is, how does the outcome differ from the outcome of doing regression on each feature value to a classification value?
That's a really good question. So again, we're working with, I'm going to go back to this picture here. We're working with a technology that is a classification technology. So what we're trying to do is set up a data set that has some number of columns that are attributes that are used for prediction, and then a labeled column that has classification labels in it. Now, let's say that with this particular phenomenon, whatever it is, I'm simply trying to decide whether it's going to go up or down next at the end of the sampled window. I'm just trying to say it's going to go higher or it's going to go lower. Well, the labels in that classification column would just be up or down, or plus or minus, or 1 or 0. But if what I wanted to do was actually try to predict what the amplitude would be next, I can't do a pure regression thing where I have, this looks like a real numbered value from, say, 0 to 1 or 0 to 0.5 here. I can't do what I could do with regression, which would be just somehow predict some real numbered value between 0 and 0.5. What I would have to do would be create buckets that go from 0 to 0.01, 0.01 to 0.02, 0.02 to 0.03, etc. And those would become my labels in the target column in the classification data. And so that would have to be how I would set up the training data. And that would be what I would be able to predict. I'd be able to predict, oh, it comes out between 0.01, 0.18 and 0.19. That would be the kind of prediction that I'd be able to make in that case.
Great. Thank you. There's actually a second question, which is unfortunately a bit longer. And so we'll probably take that one offline afterwards.
Sure.
Thank you.
I'll keep going then. So anyway, what we've done here, just to recap, is for a type of time series data that is non-cyclic, meaning you don't see periodicity at the full segment level, this is the recommended approach, which is to feed the raw data in. So we've got 150 data features just from sampling at the nanosecond level here, but then to also do some sort of hierarchical changing granularity and changing delta slide value version of calculating things that happen over time windows in the data in a way that you think captures what might be happening to the shapes. So you are definitely going through an experimental process where you're saying, I'm going to see if this way of characterizing the data gives me the kind of measurement values that I want or not. Now that's for the case where we've got something that is clearly not periodic at the full sample level. Things are a little different when you look at time series data that is periodic. So this is just one heartbeat in an EKG. But an EKG, as you'll recall from what we looked at earlier, actually looks like this, where that boom, boom, boom happens every so often on a pretty periodic basis. There are plenty of time series problems like this in the world where there is periodicity that is explained by some physical phenomenon like a heart beating. And it is often the case in those kinds of domains where there is domain knowledge available to help you characterize. You don't have to do quite as much guessing. You can use the domain knowledge to help characterize what would be the quantitative data features that you would want to include in your data set. And this is very much the case in being able to do things like predict arrhythmia from looking at EKGs. So I just wanted to point out that there are lots of problems out there that are time series data, but where you can be a little more, you can apply a little more domain expertise to figuring out what the fixed dimensional data sets should look like. And with that in mind, I'd like to show you a demo of exactly this, which is detecting arrhythmia in EKGs. This is a problem that has been something that machine learning experts have been working on for a little while now. The data set that we're looking at has 280 features in it, And a bunch of those features, like, I don't know, 30 or 40 of them, are essentially qualitative features or text-based features. So how old is the person? What is the sex or gender of the person? What was the last measurement of their systolic blood pressure and diastolic blood pressure? What is their weight? Stuff like that. But then there are hundreds of features that are actually just pulling measurements, like the different distance between P on and P off, or the distance in height between the top of the QRS complex and the bottom of the QRS complex. There are hundreds of quantitative features in this data set that reflect a certain amount of domain knowledge about what the shape of an EKG often looks like. It is a binary classification task. It's set up to say, yes, the patient is experiencing arrhythmia, or no, the person is not experiencing arrhythmia. Now, a bunch of different machine learning groups have taken a crack at this data. And what typically happens is that a team will try a simple model and then a more sophisticated model and a bigger model, and try a different approach and work through 100 or more different ways to try to model this data. And this goes on over a number of months. And then the best that team can perform is published. And the best known accuracy on this data to date had been 84.65%. And that's a good number. You know, if you could build a machine that could look at an EKG and then tell you with that kind of accuracy whether or not a patient is having arrhythmia, you can imagine how that would change the clinical workflow for cardiac patients. That would be really cool. But from a machine learning point of view, unfortunately, when building a model using the techniques that have been used so far, there's really no way to know if that accuracy number is the result of overfitting. And there's really no way to know whether that accuracy number will survive when the device that uses it is put into the field, because there's no way currently, until Brainome and the Daimensions tool came onto the scene, there's no way to know how generalized the model is that's creating that accuracy number on a validation test set. There's just no way to know. So what I'd like to show you is a demo that shows you two things. One is, it doesn't take months or even more than a few minutes with Daimensions to get to an accuracy number that's better than this. And we can, with Daimensions, know exactly whether we're overfitting or not, and know exactly how general the model is that we've built. So I'd just like to take you through a quick demo of that. So what I have is the arrhythmia data that I described to you sitting here on my computer. By the way, what you're looking at is the command line version. It's the sort of the power user version, the scientific tool version of our software. There's also a very nice graphical user interface version of the software on our website, which I'm going to encourage you to go play with. So I'm going to say, apply our software, this is the Daimensions software, to arrhythmia.csv, which is a CSV that contains the data as I described it just a minute ago, and use the column that's labeled binary class, which is the either they do have it or they don't have it. They do have arrhythmia or they don't have it arrhythmia. That's the name of the column on which those zeros and ones, ups and downs are sitting in the data. So I'm just going to, oh, actually, excuse me. I'm going to run this and I'm going to say, just give me the measurements. Don't even build me a model. Just give me some upfront measurements. And this is running for real. This is a live demo, so you can get a sense for how fast things go. I feel like I should play the Jeopardy music or something. There we go. We've got our measurements. So what do we see up front here? This is not unique to Daimensions. This is the kind of thing that any machine learning software would be able to tell you. The software found 452 instances, so we had data from 452 patients, found 279 attributes, and it agrees that it's a binary classification problem. And this is interesting. It's a relatively balanced data set. About half the patients did have arrhythmia, about half of them didn't. So the first thing I want to point out here is that this is a measure of learnability that is unique to Daimensions. It's called the capacity progression. And ideally, what we would see would be that this sequence of numbers 6, 7, 8, 8 would converge. You know, what I'd really love to see here is 6, 7, 8, 8, 8, 8. But what this corresponds to is looking at the data against a particular type of machine learning model and only looking at the first 10% of the data. How many decision points does the model need to build in order to reliably predict what's going on in the data? And we start out with 10% of the data, we only need 6 decision points. Then we go to 20 or 25% of the data, then we need 7 decision points, so a little more is needed. What I'd really like to see is this, in the ideal situation, would be that this flattens out, meaning as we see more and more data, we don't need any more decision points. The data has already shown us what its important patterns are, and we can stop adding parameters to the model. But we are seeing something that often happens in the real world here, which is that you get some initial flattening, but then you kind of look at more data, and then you sort of get into some edge cases and some things that you kind of have to memorize in order to get right going forward. And so there's a little tick up at the end. So this happens a lot. And so this capacity progression looks pretty good. It's not the ideal perfect situation, but what in life is. What we also get here is an estimate for a calculation for how many parameters would we need to build a decision tree versus how many would we need if we wanted to try to build a neural network. And here, this number is quite high. So I'm thinking neural network is not necessarily a great match for this data, but I'm hopeful about decision tree. And then, of course, I move on and I see in advance, this is before we've built a model, we've just measured. What is the risk that if I went with the decision tree, I would end up with an overfit? And that number is actually very good. That gives me a lot of hope. I want to avoid seeing 98, 99, 100% here, but 90 makes me okay, makes me feel okay. But the neural network, this really looks like a no-go. Looks like there's no way, based on our measurements, to take this arrhythmia training data and build a neural network that doesn't overfit, which is consistent with seeing this estimate of a large number of parameters potentially being needed. And sure enough, we are expecting a pretty decent generalization, meaning it's going to be pretty robust with decision trees, but really very poor with neural network. So we're definitely going to overfit. It looks very poor for generalization, and it does look like there were a lot of parameters that would need to be added to a neural network model in order to make the data make sense on a neural network. So it looks like we're going to lean towards a decision tree here. We do get the overall recommendation, which maybe there's enough data to generalize, and that's very consistent with what we're seeing in the capacity progression here. And the system is already encouraging us to just go with the decision tree for this data. The estimated times are quite short, down in the 1 second, 1 minute range. So I'm feeling like what I learned from this is this data is learnable, and I should use a decision tree to work with it. So given that, I'm going to make another call to the software. I'm not going to use measure only. I'm just going to let it do all its default behaviors and get the Daimensions software to build me a model. So again, this is happening for real. It's a live demo. Daimensions is a compiler. It takes data in and writes out Python code that captures the patterns that it found in the data and creates a predictor that's written as Python. So here we go. We've built a Python predictor that captures the patterns that Daimensions found in the training data. Very interesting here that we got just right out of the box with all default behaviors, a 77.87% accuracy, which is not the industry best, but we're getting into the ballpark there. But what is interesting is that even through the default behaviors, our generalization for this first model that's been built is better than anticipated. So I feel good about that decision tree choice because it did build us a decision tree. And the generalization ratio is making me very happy there. So now the question is, okay, it took a lot of other groups months and months and many hundreds of different kinds of modeling efforts, to get to the kind of accuracy that's been quoted as the industry's best accuracy on this problem. What can we do to get there more quickly? I am going to, make the following call to the system. I'm going to say, keep using the same data, keep using the same column as the target column for training. Definitely keep building me a decision tree because I want to keep comparing apples to apples at this point. But I'm going to go with another parameter that's called the effort parameter. And I'm going to let it start, and I'm going to talk to you about what that effort parameter is while it's running. So whenever we start a training run to have the compiler take the input data and create a Python predictor as output, we initialize a number of variables in our system. And the default, without specifying anything in the effort parameter, is to do one initialization and then run the system accordingly. But you can actually ask Daimensions to start with multiple initializations and to combine the results of its work starting from multiple initialization points. And that's what I'm doing with the -e here. I'm saying, let's do a bunch of different initializations and see if we can improve our performance. And lo and behold, bingo, our accuracy is now significantly better than what was previously achievable, which is, to my mind, a testament to how powerful the Daimensions software really is. And you'll see here that the generalization ratio, it did go down a little bit. So we're trading off a little bit of generalization, but we're still in a very strong position from a generalization point of view. We're trading off a little bit of generalization for significantly improved accuracy. This is another thing, this ability to know where you're trading off generalization for accuracy is brand new. And it's something that Daimensions brings to the game that's just incredible. And of course, we get an indication, nope, we didn't have to overfit to do that. So this is really good news. Now, I want to maybe ask one more question. We're kind of running long here, but I think I want to show one more thing here. And that is, all right, we had how many features did we have? We had 279 attributes. And some of those were qualitative and some of those were text-based, and a lot of them were numbers that we had pulled off of the EKG waveforms using domain expertise. Well, how many of those actually matter? How much of that work did I really have to do? And if I'm going to build a healthcare device, a mobile medical device that I'm going to put out in clinics or give to people to take home and wear overnight, how am I going to make it small enough that I don't have to run all the math and all of the parameters and all of the attributes to cover these 279 attributes? What if I could just carve it down to the ones that actually really matter for the prediction? So what I'm going to do is show you how that works. Again, this is something that's unique to Daimensions, to be able to do this and to be able to do it quickly and well. I'm going to add a parameter, a feature, a flag here called rank. And what that does is it asks the Daimensions software to tell us which of the attributes are the ones that are actually contributing to the ability to do the prediction. So I'm going to run exactly the same thing that I did before, but I'm going to add the -rank. Here we go. The software tells us that it's going to choose to use, Daimensions is going to choose to use only the following important columns. And these happen to be, whoops, sorry about that. These happen to be some of the domain expertise driven quantitative measurements that are taken off of the EKG readings. We don't see anything about sex or blood pressure or weight or anything showing up. These are all just particular elements that capture the shape of the EKG. So what happens there if we build a predictor with just those? This is what the software is telling us are by far the most powerful attributes in the data set or data features in the data set. What happens here is that we do get a lower accuracy, but my goodness, the generalization ratio is off the charts. It's crazy reliable. It's crazy robust. So what that gives you as a designer is the opportunity to put something out in the field that's got a 75% accuracy, but is literally going to work for everyone. So that's about what I want to finish up on in sharing this demo. I think I'll go back to our slide deck and just hand it back to you, Bertrand.
Great. Thank you, Lynn. Thanks for a great presentation. It was definitely very informative. I hope everyone enjoyed it as well. We answered a question at least during the presentation. I actually have a few more in the Q&A.
Okay.
Let me see. So one of the questions coming from Andy, it says, in your example, it looks like you are trading off accuracy for generalization. Can you comment on that?
Yeah, that is a very good point, Andy. You caught a very important idea. We do want to empower you to be able to make changes either large or small in the way that you're structuring your data, in which data features you're choosing, and how you're actually building the predictors using some of the parameters I showed you. We want to give you that ability to find the best spot on the accuracy versus generalization curve for you and your deployment.
Great. There's a second question from Sucheta. It says, what is an acceptable level of generalization? You show some numbers, but what's a good number?
So for data sets that are binary classification and have relatively 50-50, close to 50-50 class balance, a generalization ratio of 2 bits per bit or more is what you're looking for. And, you know, the higher you can go, by far, the more robust you're going to be, and the more you're going to be able to deal with data coming in from the real world. So that's for binary and class balanced cases. In other cases where you're having a larger number of classification labels or buckets and possibly have a significant class imbalance, then there isn't a hard and fast what's the best minimum number situation, but you can tell very much, relatively speaking, how varying options for either the definition of your data or the parameters you're using to build your models change the generalization ratio. And you can see relative to within that problem what looks good and what doesn't. So it's kind of a complicated answer. And certainly if you get into working with this software on your own data and you have questions about that, you can always reach out to us at support@brainome.ai we can help you interpret what's going on.
Great. I have one last question from Steve.
Okay.
In the example that we're giving, sorry, who creates the actual data features? Is that the user, or does the software create the feature for you?
Oh, that's an excellent question. So the answer is the user. The user goes through designing the data features. What we provide is this ability to very rapidly measure on any particular proposed design whether or not you're going to get good accuracy, good generalization, whether you're going to create overfit. You're going to be able to figure out which of those the data features actually are going to have an impact on the prediction you're trying to make. And so what we create is the ability to iterate very, very fast. But we are not automatically figuring out what your data features are. We're relying on you to do that. We're relying on you to generate options, and we'll help you quickly sort through which of your options are better.
Great. Thank you. But that was the last question.
All right.
Before we end our session, I'd just like to remind everyone that we'll have 3 more seminars in the application of the Daimensions during the next few weeks, although we're skipping a week during Thanksgiving week. Feel free to sign up on our website. The URL is at the bottom of the slide. We also have a parallel series of seminars that's more technically oriented for those of you interested in the math and the science behind our measurements. Thank you again for attending, and see you all next week.
Bye.
Bye-bye.